Okay. Number 1 is a hole. Number 2 is a vertical asymptote. Jason, another one of the reasons why I thought maybe you had advanced knowledge because you actually said them in the order that I have them written down. Suspicious. And a break in the graph, or sometimes it's referred to as a jump. I think the textbook uses jump. Or we call it sometimes a pop out when there's just a hole in the graph, but then at that point it exists somewhere else. You know what I mean? So like there's a hole where it doesn't exist there, and there's a hole where it exists somewhere else. We looked at both of those when we were introducing the idea of limits. And I can't think of any right now off the top of my head, but I'm sure people call these other things. It's one of those things that doesn't have as formal of a way to think about it. Yesterday we had that little activity, and I heard a couple of you really dove into it, which was great. Like, can you think of a real world place, real world situation where you would have a graph whose limit does not exist at some point, or maybe it does exist but in a weird way, and a pop out? That's one of the weird, like, could you think of, we're not actually gonna talk about this, but something that'd be interesting to think about. Think of a situation where a pop out would exist in real life. So you got a function that's coming along normally and then stops for an instant, exists somewhere else, and then continues back on its original path. Like if time was the horizontal axis, was that even possible? But could you think of a situation where it's different? Might be kind of interesting to think about. So let's just very quickly think about an example of each of these. Can somebody give me an example of a function, not the type of function, but an actual equation of a function that has a hole in it? What would that look like? I'll start us. Y equals. Okay, wait, x to the 3 minus 27 over x minus 3. Very nice. I like it. Do you agree this has a hole in it? How does it have a hole? Because if I factor this, I get x minus 3, and then I get the other stuff over x minus 3. So it's got that factor on top and bottom. I mean, x over x would be another one. It would have a hole, right? Or 2x over x. You can make them as simple or as complicated as you want. So this has a hole. Where? When x equals 3. Good. Number 2 was our vertical asymptote. Somebody give me an example of an equation that has a vertical asymptote. In MHF, the teacher gives you the equation. You find the vertical asymptote. Is it harder? If I say you come up with a question that has a vertical asymptote, is that harder? Or is it just too early to be creative? Emma, what do you think? Use the same one as above? But how could I change it slightly? Oh, there you go. So x cubed minus 27. I don't know if you meant change the top or change the bottom, but over x plus 3. Now, if I factor the top, I don't get the same factor, so I would have it very good. So the vertical asymptote here is at x equals negative 3, I believe. And you could have more than one vertical asymptote. You could have more than one hole for that matter. If I added x plus 2, I would also have a vertical asymptote at x equals negative 2. Just think about the properties, like the conditions under which you have a hole or you have a vertical asymptote, and then just write that in the function and write a bunch of other junk. Doesn't matter what the other stuff works out to, right? If you were ever asked to do this, that's what I would do, is I would start with something like a vertical asymptote, start with a factor on the bottom, and then just write other stuff around it. Make sure that you don't write x plus 3 on the bottom and the top if it's for the asymptote. And what would a break look like? In general, maybe I'll come up with this one if you want, but in general, does anybody say what types of functions? We've seen these written a little bit already. Jason? Yeah, very nice. So y equals, so it would be something like x squared plus 5 when x is less than 1, and then x minus 6 when x is greater than or equal to 1. So then that function exists everywhere because I added the equal to there. So it includes one of those points. It wouldn't have to for a break necessarily. But it's pretty clear that x squared plus 5 is a quadratic that's shifted up 5 and it opens up. And x minus 6 is a line that's way down. So when, like, they're not going to cross at that point, right? You could have, or maybe I should say this, could you have a piecewise function that doesn't have a break in it, that is continuous everywhere? Could you have that? Oh my gosh, that's fantastic. That's exactly what I would have said. Imagine you have this situation. So we're going back to grade 10 here. We don't quite do this in grade 10. We could, but we don't quite, where you have a quadratic and a linear. So if I was making a piecewise function of those two, whatever their equations happen to be, right? Kind of like this, right? Except those obviously aren't those two equations. If this value was either this point or this point, the point of intersection where they cross, it would be continuous. At any other point, it wouldn't be. That would be an interesting question to come up on a test. But where, like, you would have to solve the system. This isn't a linear system; it's a linear and quadratic system. But you would have to solve that, which is something that's within our capability algebraically. You may have never done it, but you could solve that for those 2 points, and then write the equation or something. That would be very interesting. It'd be a lot of work, but it'd be an interesting question. Any questions about any of that? Good? So those are the 3 types. So here's what we're going to do. We're going to talk, we're doing a day on sort of diagnosing those types, looking at a function. Do I have one of those 3 types? If so, which type is it? So what is it continuous? If it's discontinuous, what's causing the discontinuity? What type, where is it happening? That sort of thing is what we're exploring. So this idea of continuity, and I asked you to talk to somebody about the relationship between limits and continuity. And so we're going, in some cases at least, we're going to use limits to check if there is discontinuity or continuity, and then sort of analyze it, and then write a statement, I suppose, to talk about the continuity, whether it's continuous, what type, why it is or why it isn't, that sort of thing. That's what we're going to do for the rest of this period. Okay, so I think we already wrote this down, but we're going to write it down again. Remember, a function is continuous. Whoops. At x equals a. Did we talk about this short form before? Have you ever seen that? IFF? It's not a typo. It's not a misspelling of if. Has anybody ever seen that in here? No? Yeah, you have. A couple people? Okay. Where did you guys see it? Okay. So it means if and only if. So we won't get too much into the logic, but if you ever took a logic course or even maybe math in university or any kind of logic course, philosophy, something like that, and started to explore logic, you explore like if going one direction or if going the other direction, and if it's both, then it's if and only if. It means going both directions is like a different logical situation. Okay, so if it's true, then it's true. Like if this is true, then that will be true. And if that's not true, this isn't true, right? Anyway. So a function is continuous at x equals a if and only if the limit as x approaches a of the function f at x exists, so the limit has to exist, and that part of the definition, remember, doesn't include the function existing at that point. We can have functions that don't exist at a point, but the limit does exist. So that's only part of it. And that limit equals the value of the function at that same point. And if we can make that statement, so it says for x equals a, and we've done some testing already for particular a values, but now if we're thinking, well, what if a is like any value on the domain of the function? If this statement's true for all those values of a, then the function's continuous in its entire domain. If I can find even one point, then that function has some discontinuity. But it's probably continuous for lots of other places. Okay. All right. Everybody good? Kind of a formal definition there. 3 cases. These are not the same 3 types that we just looked at before. These are sort of 3 different cases of why something might be discontinuous. For discontinuity. If the function does not exist at x equals a, or f at a does not exist, right? So if the function doesn't exist, it doesn't matter what the limit's doing, it's discontinuous at that point. What causes a function to not exist at a point? A hole? Anything else? Possibly a break? Yeah. But for sure an asymptote, a vertical asymptote, right? Because you never cross vertical asymptotes. That's something in MHF that we talk about, in that some people, it clicks for some people and it doesn't for others. But you don't cross vertical asymptotes. You cross horizontals, but not verticals. So asymptote. Vertical asymptote. And those are both obviously if they're at x equals a in this case. So what would that look like? If I have a hole, and it doesn't matter what the graph is doing, it could be a trig function. Something like that, whoops. Or possibly, like I said, an asymptote. In this case, it looks to me like the limit exists, except that my drawing's a little bit bad and it kind of looks like those lines are going to miss each other, but that wasn't supposed to happen. So, you know, that's just a regular sine function that happens to have a hole in it. Otherwise it would be a regular sine function. So it just has a hole. So the limit would exist at that point, but it's not continuous because the function does not exist. And the other one is vertical asymptote. And even though both are going to negative infinity, it doesn't matter. It doesn't exist at that point, so function doesn't exist. Okay, number 2. What could be another type? So that one, if the function didn't exist, what about the limit? What if the limit doesn't exist? What causes a limit to not exist. If the left-hand limit doesn't equal the right-hand limit, or which would be caused by a break in the graph. Very good. Anything else that might cause that? Oops. Again, an asymptote. Very nice. Okay, so another vertical asymptote or break in the graph, maybe it would look like this. Something like that. So I have a left-hand limit that exists, I have a right-hand limit that exists, but they're different. And the function does exist at that point. In this case, I could have drawn the graph differently, but it does exist at that point. Okay. And then the third one, we said there were three. So if it's not either of the other two cases, we already said the function doesn't exist. So the function does exist. And we already said if the limit doesn't exist. So if the limit does exist, right? Does, but they don't equal each other. When does that happen? Missed. That's what we're talking about when we talk about a pop out or a jump. And that's what I was asking before. Can you think of like a real world example where that would happen? Be hard to think of with time, I think, because it would be like for an instant something would have to. And in time, what does an instant even mean? But anyway. X, thank you. Okay, so our first question to actually solve. Find the value or values of x at which f at x is discontinuous and state the type of discontinuity. And we're going to show it if we have to show it, if we have to do any work to kind of show it. And this is where that little mini activity we started at the beginning, where I was asking you to come up with an equation of a function that had a hole or had a vertical asymptote or something like that. And again, you've probably thought of this, but holes and vertical asymptotes are similar, right? Like they're similar because they both have to do with a factor in the denominator. It's whether or not that factor is also in the numerator that causes it to be one or the other. So there's a similarity. So you're going to have to be able to distinguish between the two. Shouldn't be too tricky, but I think you have to have a pretty solid understanding and sense of exactly what's going on. So when you look at that one, what's your gut tell you? Is it what kind, or is it not discontinuous at all? What do you think? John? Do you think there's going to be a hole at x equals 4? Okay, so can you explain briefly how I might be able to show that? Okay, very nice. So let's do that. So that looks a bit backwards to me, and I want to make sure that I remember the specifics of factoring, and in this case, the difference of squares from grade 10, and it's like the square root of the first thing plus the square root of the second thing times the square root of the first thing minus the square root of the second thing. I can't flip those. So it's 4 plus x and 4 minus x, not the other way around, not the way we're used to seeing it. You can't just haphazardly, randomly flip those. Do you think 4 plus x and x plus 4 are the same thing? Two plus 3 and 3 plus 2. Are they both 5? They are. Will that always work? Okay, I think the answer in that case is yes. I think 4 plus x and x plus 4 are the same thing. 4 minus x and x minus 4, are they the same thing? No. 3 minus 2 and 2 minus 3 are not the same, but they are related. What can I do to show that? What do I do? So I can factor out a negative. So off to the side here, I'm gonna probably do this in place, but if it's 4 minus x, if I factor out a negative, that means multiply both or all terms by negative and pull it out front. I get negative 4 plus x, which is negative x minus 4 if I just rewrite them now in the other way, right? So it's similar, and there is that factor we're looking for is hidden in there, but I have to pull the negative out front. I think there was a couple questions in the practice the other day that were like that required, there was at least one that required that, okay? And that is something that, we could have done back in, I mean, this is not new, it's just, we're not used to seeing it as much, are we? And as we predicted, very nice, there's our hole, therefore, there's a hole, so this is where we're stating the type of discontinuity at, x equals positive 4. I should say discontinuous at x equals 4. Okay? Next one. Remember back to grade 11, when the very first unit of grade 11 is rational expressions, not rational functions, but rational expressions. And you do a ton of factoring, and you like multiply rational expressions, and you add rational expressions, you got to get a common denominator. And the hardest part is, like, you do a lot of factoring, and, you know, if you struggle with factoring in grade 10, odds are you don't make it to calculus, but, you know, everybody's different. But factoring is a pretty fundamental skill at this point. So I imagine most of you didn't have too much trouble with the factoring part, but knowing what to do when is a bit tricky. Am I supposed to expand? Am I supposed to factor? Like, what do I do when? And again, and all you do in grade 11 with it is skills. You just do that, and it's just a bunch of practice of factoring and sort of manipulating expressions, then it's done. You don't graph them. You don't solve problems with them. You don't do anything with them in that first unit of grade 11. Okay? And now this is where we have to know when and how to employ those skills that we learned, that we started in grade 10, improved in grade 11, even used in MHF, because we learned about the properties of the functions of those kinds of expressions. So what do I do in this case? Like, how do I, like, when it's not as obvious to me in this case what's happening. So what do you think, what's your gut tell you have to do? Andrew, what do you think? So factor out the 3x on the bottom. I love it. And I'm left with x minus 5. Anything else? Factor the top. And if you're good at factoring in your head and really fast, you kind of see the factors. You probably saw that there was going to be like, oh, it looks like something's going to be in common. And maybe there is, maybe there isn't. So what's this? X minus 2, x minus 5. And so sure enough, when I factored it, now I can see in more detail exactly what's going on. So in a rational expression, we need to know that, or polynomial expressions, all of them. The expanded version tells me something. The factored form tells me something. And again, a lot of that's from MHF, but we know that we get different elements of the information from each of those forms. And so now that I've got this done, therefore, it's discontinuous where? Jason?
5.
At 5, at x equals 5. Anywhere else? Elif? Okay, and x equals 0, because it's got a vertical asymptote at x equals 0, and it has a hole at x equals 5. So see how we found both, we've done the work to show both, and we've made a statement that it's discontinuous at both those places, and why for each of them individually. Vertical asymptote at x equals 0, hole at x equals 5. Got it? Okay. This one might be obvious. What type? But how are we going to show it? If I'm doing a question where I've been asked to show it, like this one, we're going to do a bit of a formal process. But if this was informal and I just wanted to check, what would I do to see if this is continuous or discontinuous? Jason? Sub 1 into both. If I sub 1 into the entire function, I'm going to sub it into the top one because that's where the 1 goes. The 1 doesn't go in the bottom one. This is the function for the whole function. This is the expression where I would evaluate it at 1. But I want to see if the other part, where it continues. It leaves off at 1 and it continues on 1 from there. I want to see if they're the same, right? And so if they're the same, it's going to be continuous. And in that case, it wouldn't actually matter where the equal sign goes. It could be on either the top or the bottom, right? I think. And if it's different. So if I was doing this informally, I could do a mental sub and see if it works. So 1 squared minus 2 and 3 minus 1. Right? So not the same. But if it's formal, then we're going to do this. We're going to do a left-hand limit. So the limit as x approaches 1 from the left of x squared minus 2, which is 1 squared minus 2, which is negative 1, and a right-hand limit. So therefore, discontinuous at x equals 1, because there's a break, because the left-hand limit doesn't equal the right-hand limit. And we want to use the word break. Say break. Make sure you identify the type by name. Everybody okay with that? All right. One more question. This one's a bit longer, though. discuss the continuity of the following function. Give reasons for any discontinuity. So this one's going to be even a little bit more of a formal process, where we're not going to just point out the discontinuity and the type. We're also going to make a statement about the rest of the function. So here's what I'm going to start with. Do you have this written down okay? For x less than 2, what is true of this function when x is less than 2 in terms of the continuity? It's continuous everywhere. How do you know that without doing any testing? And we just know that property of parabolas. So f at x is continuous because it is a polynomial function. For x greater than 2, same thing. It's a linear function, but which is a polynomial function. So all polynomial functions are continuous everywhere. Whoops. Don't take liberties in how you write these statements, because this is a formal process where we're trying to say it all and be descriptive. Okay. I mean, I don't care what you do in your homework. You can use the little quotation marks in your homework so you don't write the same sentence 2 or 3 times. But if this was on a test, you would write that whole statement. Okay. So I have said that for less than 2 and for greater than 2, what's the point that we're missing? 2. Now I know the function exists, and I'm going to make that statement. So f at 2 exists. Because when we talked about types of discontinuity, that was one of the things. If it didn't exist at 2, if it was missing that little symbol, then I could say f at x doesn't exist when x equals 2, therefore it's not discontinuous. Like I could stop right there and be done, right? But it doesn't say that in this case. So f at 2 exists. I'm just going to put this in brackets. You wouldn't need to do this, but where it says because it said x is greater than or equal to 2, right? That's how I know that it exists. So what do we have left to show to determine if it's continuous everywhere or if it has one point of discontinuity?
Determine whether there's a limit at.
Yeah, if the limit exists and if it's equal to that point, which it would have to be in this case, then we're good. Nice. So we're going to do a left-hand limit again and a right-hand limit like we just did. So the limit as x approaches 2 from the left of f at x is the limit as x approaches 2 from the left of x squared minus 4. Okay, go ahead and finish that. nice. I got 0 and 0. Other people got that. I saw over here. We got that over here. Yeah. All right. Now we write our final statement. Since left hand limit equals right hand limit, therefore the limit as x approaches 2 of f at x equals 0, which equals f at 2. It is a formal thing. You have to write the whole thing. And therefore, because of that statement and the other ones we made above, okay, f at x is continuous at x equals 2. Therefore, f at x is continuous everywhere. We checked everywhere up to 2. We checked everywhere after 2. We didn't check. But we made this statement, but we knew that. We checked in our brains, right? Just thinking about the type of function it was. And then we checked at 2 and made a summary statement of everything. Any questions? Questions in brackets are optional. They're challenging questions. If you've got some time, if you look at the challenging questions once or twice a week, that's better than none, right? But it gives you something to think about. If you don't even answer them formally on paper, maybe if you're in MSIP with somebody else taking calculus, you could sit down together and try it. Just talk about it. Would be really interesting. Though those two aren't super hard. One of them has a little bit of work to it. The other one just kind of makes you think about it. So I think they're good questions, even just to read. Any questions?